Quantum mechanical simulation captures changes in electronic structure such as bond forming and breaking, charge transfer, and other behaviors that are hard to model with molecular mechanics. However, its high computational cost limits its usage to at most a few hundred atoms. When we want to simulate something bigger, for example, in a solvated protein system, a multi-scale simulation approach can be beneficial. One such approach is the hybrid QMMM method that benefits from the accuracy of QM methods and the efficiency of MM potentials. In a typical QMMM simulation, the active site atoms are treated with QM, and the rest of the system, including water solvents and their periodic images, is treated with MM. Setting up a QMMM simulation is a challenging task even for simulation experts. To facilitate this type of simulation, we have developed QMMM Interfacer that generates simulation inputs for QMMM simulation, where non-trivial setups can be done interactively with a GUI. This video demo will demonstrate the general functionality of the QMMM Interfacer module in CHARMM-GUI. For the sake of convenience, we will abbreviate QMMM Interfacer as QMI. The protein system we will use is dihydrofolate reductase, or DHFR. DHFR is an essential enzyme in the synthesis of purines and catalyzes the conversion of dihydrofolate into tetrahydrofolate using NADPH as an electron donor. This enzyme has also been widely studied as a test system in computational enzymology. To begin, go to QMMM Interfacer, type the PDB ID 1RX2, and click Next. We want to include the protein, both the FOL and NAP ligands and water, and click Next. If we want to modify the protein structure, this is where we would do it. To learn how to use the structure manipulation options, please see the video demos for PDB Reader and Manipulator. In this case, we only modify the protonation of two histidine residues, HIS 114 and 141, to HSP. Then, click Next to generate a CHARMM-compatible PDB file. Once done, you should view the structure to ensure that it was read correctly. We solvate the protein and add ions to mimic the physiological conditions. If you have any questions regarding this step, please see the video demos for Solution Builder. With default settings, we build a solvated system and begin QMI-specific ligand modification. At this stage, we can modify heterochains, mostly ligands, that you selected from PDB Reader. Click the ligand you want to modify, then open to import the ligand into the Marvin.js sketcher. You can modify the ligand and decide how to embed ligand coordinates. Ligand atom coordinates are initialized by finding the maximum common substructure between the input PDB and the output QMI ligand structures and aligning the coordinates in the maximum common substructure. With the first ligand embedding option, atoms are included in the maximum common substructure only if the atom type and bond orders match. With the second embedding option, only atom connectivity is considered, which may result in more atoms being included in the maximum common substructure. In general, matching element is the safer choice, but choose matching any if you want to maintain the coordinates from the original ligand as much as possible. In this example, we choose matching any. Next, click Update Ligand to embed the modified ligand into the system using the maximum common substructure finding algorithm from RDKit. You can see the updated ligand coordinates in the pink-colored ball and stick model. Next, click Parameterize to parameterize the modified ligand. If you choose the CHARMM force field, it will be parameterized using cgenFF. If you choose the Ampere force field, the ligand force field will depend on your choice of GAF or GAF2, and will be parameterized using antechamber. If parameterization is successful, you'll see a green check, otherwise a red X will be shown. Repeat the process for the second ligand. When all ligands are parameterized, click Confirm Force Field to proceed. On the next page, the system you built is displayed. Protein backbone atoms, bulk water, and ion visibility can be toggled in the molecule viewer on the left. To complete QMMM modeling, you must select which atoms will be included in the QM region. You can select atoms by specifying the segment ID, residue name, and residue ID. Specific atoms from the residue can be added, or you can use the all or sidechain shortcut selections. To include atoms from another residue, click the Add Atoms button. For ligand residues, there is the additional option of selecting atoms in Marvin.js. This option causes the ligand to be opened in Marvin.js, where atoms can be selected graphically and confirmed with the Update button. Repeat the process until the entire QM region is selected. The total charge of the selected QM region will be interactively shown here to help decide the charge of the QM region. The QM region can be visualized by clicking the Show Selected QM Region button, which causes selected QM atoms to be colored magenta in the molecule viewer. Next, you must choose a QM method. Currently, QMI only supports semi-empirical methods and the CHARMM and AMBER simulation packages, but this will soon be expanded to include various ab initio and DFT methods and more QM simulation packages. The currently available simulation packages are shown on this slide. When cutting a covalent bond to introduce a QM-MM boundary, QMI currently supports the H-link method, where a link hydrogen atom is inserted between any QM-MM boundary that cuts a covalent bond. This method caps the QM system. Additional treatment is still needed to prevent the overpolarization of the nearest MM atom. After typing the desired total charge of the QM region, click Distribute Charge to distribute any residual charge to the nearest MM atoms. These links are automatically detected based on their MM connectivity, and a proposed charge distribution is shown below when you click the Distribute Charge button. By default, QMI evenly divides the partial charges into the end links. However, you can override any default partial charge by modifying the value in its corresponding text box. When choosing AMBER for simulation, you can select the charge distribution method in the corresponding drop-down menu. Please refer to the AMBER user manual for details about the charge distribution methods. On the next page, we can download the generated QM-MM inputs. The enclosed README file demonstrates how to use them, but you can ask any additional questions to the CHARMM-GUI forum.